Let's do problem number 10 first, because it's a little easier than it looks, and sometimes those can be the tricky ones. We're assuming that we have a hold time of callers that is normally distributed with a mean of 5.4 minutes and a standard deviation of 0.9 minutes. We're going to determine the percent of callers who are on hold for more than 5.4 minutes. Now what you notice over here is that they are asking us what percentage of callers are on hold for more than the mean. The mean is 5.4 minutes. And no matter what the standard deviation is, the number of data values above and below the mean is always 50%. So this answer is just going to be 50%. All right, let's take a look at the next one. I think we did this problem in the video lecture, so let's move on to a different one. Here we go. A vending machine is designed to dispense a mean of 7.6 ounces of coffee into an 8-ounce cup. If the standard deviation of the amount of coffee dispensed is 0.4 ounces and the amount is normally distributed, find the percent of times the machine will dispense between 7.3 and 7.7 ounces of coffee. All right, I always like to have a picture, so I'm going to draw something out here. Here's our normal distribution, and the mean right there is going to be 7.6 ounces. And I'm going to exaggerate this picture a little bit for spacing reasons, but we are being asked how much data falls between 7.3 ounces and 7.7 ounces. So we are wondering, what is this area under this curve between 7.3 and 7.7? Now to do that, we need to find z-scores for both 7.3 and 7.7. So let's find some z-values. For 7.3, our z-value is going to be 7.3 minus 7.6 over the standard deviation, which they told us was 0.4. That's going to give us negative 0.3 over 0.4, which turns out to be negative 0.75. All right, I'm going to move this down a little bit to make a little bit of room on my picture. What we just found was that this z-score here is negative 0.75. Okay, we're going to look that up in the table in a second, but first let's calculate our other z-score. Let's calculate our z-score for 7.7. That would be 7.7 minus 7.6 divided by 0.4, and that turns out to be 0.25 for that z-score. So what we just found was that the z-score for this 7.7 up here is 0.25. Now what we're going to do is we're going to look up this z-score in our table, and we're going to look up this other z-score in our table. We're going to subtract those two values that we get from the table, and that's going to give us the area that we want. Let's actually do it. First, I'm going to look up negative 0.75 in my first page of my standard normal table because it's a negative z-score. If I look up negative 0.75, that would be right here. It's 0.2266. What that says is that this area in here is 0.2266. Okay, great. Now let's look up our other z-score, which happens to be positive, so I'm going to use the second page. And we are looking for 0.25, which appears right here in the table, 0.5987. So we're told that this area over here is 0.5987. But what we really want is the area in between those two z-scores. And that area we're just going to have to calculate by subtracting 0.5987 minus 0.2266. And that turns out to be 0.3721. If we want to turn that into a percent, it's going to be 37.21%. So that's what we need to enter into my math lab, and that is going to be the correct answer. What I want to show you though is a way to do this problem using a little bit of technology. So let's open up our calculator, and we can actually do this whole thing in one line of work. So what I'm going to do is use this DSTR, this distribution option. So I'm going to hit second and that button. We're going to use this normal cumulative distribution function, normal CDF. I'm going to hit enter. And whether you have the old school calculator like me or a new one, the first thing you're going to enter is the lower limit of this interval that we're looking for. We're looking for the amount of data between 7.3 and 7.7. So our lower limit is going to be 7.3. We're going to put a comma, and then the upper limit is going to be the next thing we enter, 7.7, and then a comma. Then we're going to put the mean of our distribution, that is 7.6 in this case. And finally, we're going to put the standard deviation of this distribution, which is 0.4, and your calculator is automatically going to spit out the final answer that we got for this problem. Now that makes this problem seem almost too easy. Feel free to use this technology, but also keep in mind that we do have to show our work sometimes, and if you need to show your work on a problem, you're going to have to know how to do this using the tables. Let's jump ahead a little bit. Let's go up to problem 16, and we're talking about ripe watermelons grown at a particular farm. They're normally distributed with with a mean of 50 pounds and a standard deviation of 2.1 pounds. Let's determine the percent of watermelons that weigh between 47.49 pounds and 53.49 pounds. Feel free to do this with the tables, but what I'm going to do is just type everything that we need to type into the calculator and see if we can get the right answer that way. So I'm going to again hit second and this button here so that I get this distribution option. We're going to use normal CDF. I'm going to hit enter on that. The first thing that we're going to enter is the lower limit on the number of pounds for these watermelons. That's 47.49. Then we're going to enter the upper limit, that's 53.49. Then we are going to enter the mean, which is 50 in this case. And finally, we're going to enter the standard deviation, which is 2.1. We get an answer of 0.8357. They want this written as a percent, so I'm just going to go ahead and do it. I'm going to do 83.57, and I'm going to check the answer, and that is correct. Again, feel free to do this, check your answer using the tables, but that calculator function can save you a lot of time in this section. And I'm just going to really quickly run through one more problem. Let's clear this out and read what's going on here. The annual daycare cost has a mean of 7,000 and a standard deviation of 500. We have 300 families that we're sampling from, and we're asking how many pay more than $6,810 annually for childcare. So what I want to do is show you how to do this on the calculator. The first thing we want to do is find the percentage of families that are paying more than $6,810 for childcare. To do this, I'm going to again hit my distribution button. I'm going to choose normal CDF. The lower value that we're looking for here is $6,810. We're looking for the percentage of families that pay more than that. So what is our upper limit going to be? Well, we can't type infinity into this calculator, so we're just going to have to type in a really big number like 9999999 or something like that. So now we're looking for all of the families who pay between $6,810 and whatever this is, over $9 million. So that gives us our lower and upper limits. The mean of this distribution is 7,000. And the standard deviation of this distribution is 500. So if we hit enter on that, that tells us that 64.80% of our families are paying more than $6,810 annually for childcare. But we're talking about a random sample of 300 families. And the question is, how many of those families do we expect to be paying more than $6,810 annually for childcare? Well, out of those 300 families, we're saying that about 64.80% of them will be paying more than that amount. So to find the number we're looking for, we're going to take 300 and we're going to multiply it by our previous answer. Our previous answer was 0.6480 and so on. If we hit enter on that, we get 194.4 families that we expect to be paying more than this amount for childcare. We're going to round that to the nearest whole number, that's 194, and that is going to do it for this section. I think between the problems that I showed you how to do on the calculator and the problems that I showed you in the video lecture, that you should be able to finish this thing up. As always, let me know if you have questions, but I hope that this helped you out, and I will see you next time.